This is a description of a Matlab script called Introduction to Matlab, and I'll be describing the different steps and things that you should consider as you execute the script. The script is available on the course schedule, so I would recommend that you follow along as you watch this video and actually do the different steps. So in terms of the script, it has several different sections. So in the script, the array manipulation is the first set of commands. Each command is in a separate cell in the script. And to execute the cell, options are to right-click and do evaluate current section, or you could hit Control-Enter. Another option is to highlight the commands, and in that case, instead of executing everything in the entire cell, you can execute just the selected area, and in that case it's evaluate selection, and an alternate hotkey is just F9. So as I go through the script, I'll probably be using either the menu commands or the hotkeys, but that's basically how things are happening, and then the results are displayed in the command window. So for this first cell, if I just do Control-Enter, I get the result 5. In the next cell, notice that the first cell, the result was not assigned to any variable. So in Matlab, by default, the variable it is assigned to is given the name answer, lowercase ans. And looking over in the workspace, it's basically a 1-by-1 array or a scalar, and it's of class W. And then in the second cell, if I execute that, here I get a second variable x since I've done the assignment operator, the equal sign. So now the variable x has a value of 5. In the next cell, if I take the value of x, add 1 to it, I get a result 6, but I've not actually assigned it to a variable. So if I would want to assign it to a variable, I would have to put x again on the left-hand side of the equal sign to make the assignment. And now x is the value of x is replaced from 5 with a 6 value. In many languages, you can do this construct of x equal x plus 1 by doing x and then plus equal 1. And the advantage of that is you do not have to repeat the value x. But if I do that, and here I'm just going to do evaluate selection, you can see that I'm getting an error message in the command window, and the error messages are in red. And in this case, Matlab is inferring that I probably meant to do what was done in the previous cell, x equal x plus 1. So again, that's just not something, if you've used other languages that have that syntax, that's not something that is possible in Matlab. One advantage of it is that in many cases you have to, instead of just a simple variable x, this might be a very complex expression. So this syntax eliminates the need to have to repeat the expression, so you get really more information in one line of code. So this is a feature that would be nice if Matlab had, but currently does not have. To actually redo that, currently it has a value of 6 because I increased from 5 to 6. So if I execute again in the next cell, I get a value where x now has a value of 7. And then here x is going to have a value of a row vector with the elements 1, 2, and 3. So when I execute that, the only difference now is instead of size being 1-by-1, x now is a 1-by-3 or row vector. Alternatively, I could create x as a column vector, a 3-by-1 column vector. And again, if you look over in the workspace, you can see that x is now a 3-by-1. Instead of actually having to enter each element and hit return, an alternate way of doing that would be to use the transpose operator. So with the transpose operator, I can again create a column. So I can enter it as a row vector, but then by using the transpose operator at the end, it basically converts it into a column vector, which is what I wanted. Another alternative is to use a semicolon symbol, and what that does is the semicolon is the same as hitting the return key in this cell and forcing it to be another row in the array matrix. So if I do that, I also get the 3 by 1 column vector. So here, if I want to just see what is the current value of x, it has the values 1, 2, and 3. If I want to change one of the values, I can specify it by indicating what is the index that I want to change. In this case, I want to change the second element, and that's indicated by within parentheses the value 2. And then I can make it a change by just setting the second value of x to the new value 5. And when I do that, again, I'm hitting Control Enter to execute the cell. And now I get a result 153, so it has made the change. In Matlab, it's in addition to just manually inputting the data, other ways of actually getting values into your arrays. There are ways of reading data files and other more complicated things, but in many cases, beyond just manually entering the value, it's convenient to be able to automatically generate a series of values that have some type of structure to them that allows them to be easily generated. So one example of that is using the increment operator, and in this case it's indicated by using the symbol colon. And what this does, I'll go ahead and execute it, it enters the values 1 through 5 in increments of 1. If I want to change the default increment, which is 1, to some other value, then I use a second colon, and I put the increment value in the middle of the expression. So in this case, it's entered it as an increase of 0.5. And as a result of that, if you look in the command window, all of my previous commands had integer values, which were just indicated with the integer value. But in the case of real values, the values are floating point, and Matlab in the command window by default represents the value with 4 digits to the right. Internally, it actually stores the value with more significant digits, but for display purposes, by default, it has a value of 4, and there are ways of changing the format so the command window can display more than just a standard 4. So if you want to see more of the digits, that is possible. Going back to the script, another way of, instead of assuming the default value of 1, this is an explicit use of 1 as the increment. So again, I get the original 1 through 5 increment. Here's an example. If I want to increase in increments of 2, I get 1, 3, 5 all the way up to 15. So that's if I want to get increasing. And if you wanted to get decreasing values, then you would use -2, and then it would decrease from the starting point to the ending point. And the ending point then should be less than the starting point for that to work. Another possibility of structured data to create is an array where all of the values are all the values are the same. So in this case, if a is equal to 1, I hit return, I get a value of a row vector with 5 1s. I can do the same for zeros, get a row vector with zeros. If I want to get instead of a vector, if I want to get a matrix, I can get a 2 by 3 matrix of all zeros. And then if I want to change an element from something other than 0, in this case the first row second column value, the 1, 2 value, I can change that to 3. And if you look at the command window, you can see that that value now is 3. Another option is if I want to take the values, and originally they're going to be values of 1 through 5, all values of 1. If I want to add 3 to that value, I can go ahead and do that, and I get now a matrix of all 4s. I could also multiply by some value and multiply times 1, so I would get that value. Okay. I can also generate an array of random numbers. And in this case, the random numbers are between 0 and 1. And if I execute it a second time, so I'm in the same cell, and I'm going to hit Control Enter, I get a different value. So every time I do that, I get a different set of random values. And this way of constructing arrays is going to be very useful because for a lot of applications, we would like to essentially simulate different random possibilities. So we'll be using this random function to generate array data. In many cases, though, in addition to just randomly generating the data, we would like random data, but we would like to be able to recreate the data. And in this case, every time I run the RAND by itself, it's just going to give me different values. So if later on I'd like to be able to recreate the sequence of random values, it would be convenient to be able to control that. And in Matlab, the way that that can be controlled is to use the random number seed generation command, and that's the function RNG. And then RNG is given a seed value, so you can put essentially any number there, in this case 2017, and any integer number is fine, but as long as you use the same integer number and set the seed, then every time you call the RAND function, it'll give you the same value. So in this case, I'm going to execute it with the seed 2017, and I get that set of random values starting with 0.021 and 0.93 as the last one. And now if I call it again, I'll get a different value. But if I wanted to go back and recreate the original value, if I just basically execute the same seed setting of 2017 and then call the RAND function, I get my original 0.021 and ending in 0.93 set of random numbers. And then if I do it a second time, I get the same second value. So it's not really random, it's what's called pseudo-random, depending on what the seed point is. So if I switch it to 2027, I would get another point, and then just like before, I would be able to generate the same sequence of essentially pseudo-random numbers from that point. If I want to generate a random integer value, then there's a command called rand_i. So the only difference here is this I at the end. So instead of getting a random real number, I get a random integer, and the range of the integer is indicated by being any value from 1 up to whatever the argument is for the rand function. So whereas with the rand_i function, the rand function, the two input arguments indicated the size of the resulting array. In the rand_i function, it indicates what is the maximum integer value. So in this case, when I execute this, I get a random number 2. If I do it again, I get a random number 9, and all those values should be between 1 and 10. If I get a random number between 1 and 100, in this case 24, and so on. If I do it again, get 85, 87, and so on. So generating random integers is also convenient. There's another function, and these are all standard library functions in Matlab. They're all part of the Matlab language. Another very useful function is called random permutation, which is indicated as RANDPERM. And just like with the rand_i function, with the random permutation function, the input argument is the maximum size of the array of the result. So in this case, I'm getting a random permutation of the integers from 1 to 5, meaning that I'm going to have a 5-element array, and the values of 1 through 5 are going to appear exactly once in that array, but the location in the array that they appear is going to be random. And there again, an example of the use of random permutation is if I had a series of, say, people that were going to be arriving to an office, and I wanted to generate a random arrival of the order of arrival for these customers, then I could use random permutation as a way of kind of mixing up the order of arrival. So again, that's a very useful technique. For the rand_i function, instead of just generating a single value, if I want to generate, say, a 2x3 array of random integers with a maximum value of 100, then I can add a second and third input argument to rand_i, indicating the size of that array. And when I do that, I get a 2x3 array with values ranging from 1 up to 100. So this is just a short introduction to the different standard generating functions that give us standard array values. And in the subsequent scripts, we'll be using these to do a lot of additional things, and also in the basic concepts. And what is being done for homework number 1, you'll have an opportunity to explore more applications of this. Our second topic is going to be on multiplication and addition. And the two techniques that we'll be looking at are first matrix multiplication. And in matrix multiplication, the idea here is we use the standard techniques of linear algebra. We're given two arrays. The inner dimensions of the arrays have to be the same for the multiplication to occur. And then the other technique is element by element multiplication. And here the size of each array has to be the same, not the inner dimensions. And in Matlab, it now has broadcast capability. And what that means is, as long as the two arrays have the same compatible size, then the array that's smaller will be extended or broadcast so that it has the same dimension. So in this slide, B is just a row vector, but since the number of columns is the same as A, it's compatible. So the number of rows are then just duplicated. So each row of B is duplicated a total of m minus 1 additional times so that it has the same m by n value as the A matrix. And as a result of that, we can have element by element multiplication. And in Matlab, that's indicated by the red dot before the multiplication symbol. And then we get a result C that has the same dimension. And one thing that the following script is going to be illustrating is some applications where, because of compatible size issues, we're actually getting an error and not able to actually multiply element by element. So the following cells will actually illustrate that. So first I'm going to generate some data. In this case, I'm going to create an A matrix. And this is a 2 by 3 matrix with values 1 through 6. Notice when I did it, it actually executed into the command window. It actually displayed the value. Since I'll be creating a lot of data, many times I don't want to actually see all the data. So if I don't want to see the data, I could create the A matrix by using just the semicolon command. And what that does is it suppresses output. So when I execute that, I don't actually get that as a result. So I'm going to do the in this case F9 because I've selected this. So when I hit F9, or if I right click, I would do evaluate selection. It shows me what I did, but nothing's actually displayed to the command window, so it doesn't display this result as an A matrix. Here I'm going to create a B matrix. I want it to be a 3 by 1 column, and I'm using the transpose operator to make it into a column matrix. And again, I'm going to hit F9, and this actually then displays as a column vector. And the reason it's displaying, as opposed to in a case where it didn't display, is here I don't have the semicolon at the end to suppress the output. And then here is a C matrix, and it's a 1 by 2 row matrix. So I'm going to F9, execute that. So now if you look into my workspace, I have my previous data, but now I have this A matrix and these B and C vectors. Notice that I've indicated the matrix as an uppercase value A, and I've indicated the vectors as lowercase. And in Matlab, uppercase A is different than lowercase a. Each can be separate variables, so the case is actually significant. Other languages, that's maybe not the case, but in Matlab, whether it's upper or lowercase gives me different variable names. So it's not part of Matlab, this convention of vectors being lowercase versus matrices being uppercase. I do it just as a personal way of allowing me, when I look at my code, I can see if I intended the array to be a matrix or a vector. And sometimes a matrix, that normally has multiple rows might default to a single value, but it's really just a degenerate case of what should be a multiple row array. So that convention, I think, is a convenience that really helps sometimes avoid confusion. So this first example, I'm going to take the A matrix and I want to add 2 to all the elements. And in this case, the compatible sizes are enforced. If we think of the 2 as being a 1 by 1 array, then that 1 by 1 array can be expanded to have a 2 by 3 matrix. So essentially 2 becomes a 2 by 3 matrix with all 2 values. And in that case, it's compatible. So element by element, the elements of A can be added to the values in that 2 matrix. So when we do all of that, we get the original A matrix with 2 added to it. Notice that I haven't done any assignment, so I haven't actually changed the value of the A matrix. Here, similar idea with multiplication. Again, the 2 value, thinking of it as a scalar to start with, is going to be broadcast so that it has the same dimensions as A, so that it can be multiplied element by element. Notice in this case, I don't need to include the dot multiplication symbol, even though I'm ultimately doing element by element. And the reason is that this is such a common thing that it just simplifies not having to indicate the dot matrix. So when I do this, I get 2 times the original A matrix. Again, I haven't changed A, so it's all the original A matrix that was defined up here. This next example is a case of matrix multiplication. And here I'm going to take my original B vector, and my B vector was a column vector. So if I take the transpose of the original column vector, that'll turn it back into a row vector that has now the dimensions of 1 by 3. And then I'm going to multiply that matrix multiplication with the original B, which is a 3 by 1. So in this case, the inner dimensions are 3, and I end up with a scalar result. And that scalar result of 56 is just the product element by element of the values in B. That's the same in linear algebra as the dot product. If I do the opposite thing and take the original B and then take the matrix multiplication of that, here the inner dimensions are 1, so I end up with a 3 by 3 matrix. And that's just a product of the corresponding elements in B. So it's a 3 by 3 resulting matrix. Another type of matrix multiplication that's possible is a 2 by 3 matrix, and that gets multiplied times B, which is a 3 by 1. Again, here the inner dimensions are the same, so I end up with a 2 by 1 matrix, which is just the sum of the products of each row of A and B. Here's an example. If I execute this, I get an error, and the reason is that here the inner dimensions are not the same, so matrix multiplication fails in this case because I don't have the correct sizes. Here, if I go the other way and take C times A, here is a case where the inner dimensions now are correct. So I will get, in this case, a 1 by 3 row vector as a result. Here, if I take the transpose of A, instead of being 2 by 3, it's now a 3 by 2 matrix. If I take the transpose of C, it's a 2 by 1. Inner dimensions are the same, so I end up with a 3 by 1 result. If I did an element by element multiplication here of A times the B vector, then executing this I get an error. And the reason is that the dimensions are not compatible. Even though there's a 1 in the B, the 3 would have to be in the second position as opposed to it being in the first position. It's not compatible with the 2 element in this expression. So in this case, instead of taking B, if I take the transpose of it, now I have a 1 in the B, and then the 3 for the B is now compatible with the 3 in the A, so it can be expanded. So in this case, it works in terms of element by element computation. The next example is another case where I do get an error. Again, it's basically for the reason that it's not compatible. The 2 is not in the second position in A. A has 2 in the first position, so it's causing an error since it's not compatible. So if I take the transpose, now I have a situation where I have compatible sizes, and I do get this result. And again, you could do more extensions of this, but this is just to give you an idea. This is something that eventually will become pretty routine in terms of your manipulations of the arrays in Matlab. Prior to the ability to do broadcasting where it would expand, up until about 3 or 4 years ago in Matlab, it was not possible to have it automatically expanded to be compatible with the arrays. So in order to do, for example, this type of calculation, you basically had to take the C vector and do the matrix multiplication with a 1's vector to make it so that this value had the same size as the A matrix. So when I do this through matrix multiplication, the C column vector, since I'm taking the transpose of C, the 3 and the 5 have been duplicated 2 additional times. So this is sort of the old way of doing this broadcasting. And then if I put that here inside parentheses, it'll give me the same as this result here that was done automatically. And when I do that, I get that same result. So you can see the advantage of several years ago when Matlab added this broadcasting capability. This can be done sort of in a much cleaner manner as opposed to having to do this. So it used to be that in Matlab code, you have all these things, and to me it was just, made Matlab code very confusing. So this is a really nice addition and change. Other languages like Python have had that for a number of years, and it's nice that Matlab now does have that same capability. This is another example where these have compatible sizes, and we end up with a 3x2 matrix. Here the compatible sizes are basically there's a 1 in each of the 2 arrays. So in terms of the rules of compatible sizes, it allows the values to be expanded and be able to be multiplied on a element by element basis. Okay. And then finally, the last thing I'm going to do is I would like to kind of clean up my workspace, because I'm going to start the last section where I go through an example on minimum distance location problems. And what I'd like to do is eliminate all of the variables in the workspace. And also I would like to clean up the screen here. So the first command, CLC, I'm going to do F9 to execute it. What that does is just clean up everything in the command window. And then the next command, clear all, when I F9 that, it'll actually eliminate all of the variables in the workspace. So essentially now I have a clean working environment. For this next example, I'm going to be looking at the problem shown here where I basically have 3 points, 1, 2, and 3 indicated in the P matrix. And that P matrix can be indicated in Matlab as just a standard matrix array. And then I have a single point X that can be indicated as a 2-element row vector. And what I would like to do is generate the Matlab commands to be able to generate the distance from this X point to each of these 3 other points and have it returned as a 3-element column vector where each element is the corresponding distance from X to that point. And I'd like to be able to do that, and as you'll see, you're able to do that in a single line of Matlab code using the ideas of compatible sizes and matrix multiplication. So I think it's a nice example of Matlab capabilities that we'll be utilizing very shortly when we look at the facility location problem. Because the obvious idea here is that given the distances here, I would like to maybe, if I'm able to change the location X, find a point such that, for example, the sum of these distances is minimized. And assuming that the distance corresponds to maybe the travel distance from this location to all these different points, which maybe are cities, I would like to minimize the total travel distance. So that's a first example of the network design problem that we'll be looking at. And we're going to first generate the P matrix and the X point. So the first step in terms of looking at that calculation, I want to be able to take the difference between the point X and the 3 points in P. I can do that by just X minus P. Because X and P are compatible, that is done automatically. And then the next step is to take each element and square it. So if I go to Matlab and just do the exponent operation, which is the caret, you would normally think that that would work in most languages. But when we do it in Matlab, we get an error. And the reason is that Matlab is actually trying to do matrix exponentiation, which is something that actually requires that the matrix be square. That's something I've never used at all in any logistics application. So that's something that is really a pure linear algebra application. In Matlab, what we want to do is be able to square each element of the array. And to do that, we have to use the dot symbol to indicate that we're doing element by element exponentiation. And when we do that, and execute it, we get our intended result, which is just squaring all of the elements of the previous difference calculation. And then looking at the formula for calculating the Euclidean distance, the next thing we would want to do is to be able to take the sum of all those squared differences. And if we do that, we can use the sum command in Matlab, which is just sum. And here it's just a single input argument, which is this previous value that we did. And when we do that, we end up with a result, which is a 1×2 row vector. And what's happened is it's taken this result here, each of these columns, and just summed up all of the values in the column. But if you look at what we're trying to do, it's actually not what we're trying to do. We don't really want the sum of all the different points. We want to take the sum for each point. So what we like to do is actually sum each row. So we would like to get 1 + 4, 25 + 4, and 4 + 4. But Matlab by default is actually summing each column. So the way that we can force Matlab to sum the correct way is to indicate, using the sum function, a second input argument. And that second input argument would be the dimension over which we would want to do the summation. So by default, the first dimension of every array is the column of the array. So if we do the 1, we get what we got before by default. So if instead we want to sum over the second dimension, indicated by 2, we have to indicate that as the second input argument. And when we do that, we get the intended result, which is the sum of each row in the resulting array. And then next step of the Euclidean distance formula is to calculate the square root of each of these sums. And we can do that by using the square root function. And at that point, it's essentially done everything we want. We basically have now the Euclidean distance from x to all of those points. So we're at this point, we've kind of solved our problem. And really the last thing we really need to do then is assign it to the variable d. So we've done our objective of actually getting within one line of code an actual result d. So we've built up all of the different steps needed for that. And to be able to make it very useful, what we would like to do is to make it flexible so that instead of using just the indicated x value of 2 and 3, it would be nice if we could make it so that we could very conveniently change the x value to have different values. And to be able to do that, we use a construct in Matlab called anonymous functions and function handles. And the syntax for that, and again, I would recommend looking at the basic concepts where it's talked about in a bit more detail. So assuming you've looked at that also, essentially what we're doing here in this next cell is defining a function handle. And I use as a default value fh for function handle, just so I know that when I look at my workspace, that is a variable that is representing a function handle. And the syntax of a function handle is such that if we use the @ sign or ampersand and then indicate within parentheses x, the variable that we want to keep as a variable and not an actual value, because previously we've defined x to have a value 2, 3, but in this function handle definition, it's going to ignore any previous value that x had. And we could actually use, instead of x, we could call it y or give it any other variable name. But I used x just to illustrate that it doesn't affect the current value of x in the workspace. As long as we put whatever symbol we put within these parentheses, then after that, within the expression, that same value x is going to be treated as a variable. And then if you look at the next step, when we call the function handle, we can use any value for x and any input argument, and it'll use that in place of the original x value wherever x appears in the resulting expression. So it's a very handy construct. So when I go ahead and create that, you can see that at the command window it says now there's a function handle with value, and it shows what this is. And also if you look into the workspace, it shows what fh is. One thing to note with a function handle is that the matrix P, that 3×2 matrix of existing point location values, when you define the function handle value, it takes whatever the value p has at that point in time and codes it into the function handle. So later on, if we would go and make changes to the p matrix, the function handle wouldn't be aware of any changes to p, and it would use the value of p that was in force at the point where we actually created the function handle. So if we wanted to be able to update and use new values of the function handle, we would want to have to go and re-execute this call. So we'd go back up to this cell and then re-execute and redefine this function handle. In that case, the function handle would now have the new p values within it. But everything except for the variables that are in parentheses all are kind of a snapshot of point in time at which the function handle is defined and then don't change after that. And in most cases, that's really the behavior that you do want. You don't want it to be changed. You want everything to be fixed except for the single variable argument. So when we use it, if we take our original x value, so here x is now referring back to the original 2, 3 value, we get the original calculation of d, so this just matches up. But what's nice now is we could take the x values and just double the coordinates, and we get this result. We could also define the 0, 0 point, so looking at that figure, that would be off in the corner. If we wanted to find the distance from that corner point to all 3 points, we can put 0, 0, and we get that value. Here we get 4, 3, another set of values, so we get a lot of flexibility with the ability to be able to do that. We may want to, instead of getting 3 separate values, if we want to look at the problem of being able to find out what point has the minimum sum of all the values, what we could do is add summation to our function handle definition. So what I've done here is I've taken this original function handle definition and just put that as the input to the sum command. And now I'm going to go and redefine this function handle. So now it's a sum of all of the distances. And when I go back and look at the 4, 3 point, instead of getting 3 values, I get the sum of all 3 of those values. One reason that that is useful is that I can now use this function handle and do some types of optimization. So in this case, what I would like to do is pick a random starting point. So in this case, I'm going to pick the point 0, 0 as a starting point. And from that starting point, I'm going to use a function which is part of Matlab called fminsearch, which does an optimization. It's sort of like using solver in Excel spreadsheet. And that starting point, together with this function handle, what this min search function does is takes that starting point and then tries to find other points that reduce the value returned by this function handle. And it keeps doing that until it can't find any further improvement. So if I do that, I end up with this result, and I get a 0.4 for x and then 2.7. That value then corresponds to the point in that space that has the minimum sum of distances. So if I want to see what is then the corresponding value, it's 9.1962. And when I compare that to this value, which was from the point, I think 4, 3, it had a value of 9.21. So that is a lesser number, even though it's pretty close to what the optimal is. So 4, 3 is pretty close to where the optimal location is, but it's not quite the optimal location. If I had picked another starting point, instead of 0, 0, if I picked 100, 100, I would get the same result. And it turns out almost the same result. If you notice, there's a slight difference here in this last digit. And the reason is that fminsearch is a numerical technique that doesn't guarantee, because we're dealing with real numbers, it doesn't always guarantee exactly the same real number, but they'll be the same within some tolerance. In this case, it turns out because of this particular problem, it has the feature that it doesn't really matter what starting point we pick, we'll actually get to the same optimal point. That's not something that's true in general. It just happens that for this particular problem, we get that behavior. If we look at 0, 0, our original starting point for the optimization, for this original optimization, it had a total distance value of 14, which is much higher than the 9.1119 optimal value. So that's not as good of a point. If we compare this to the optimal, again, we get that same 9.19 optimal result. again, starting at 100, we get the same value. Yeah. And then, so here, starting at 0, 0, we get the same value. So again, this just shows that we can duplicate this result. What if instead of starting with a row vector indicated 0, 0, what if we weren't really paying attention and somebody entered a two-element array, but instead of as a row vector, it was entered as a column vector, and we're going to force this to be a column vector by just using the transpose operator. Well, if we did that, we'd execute this, we actually get an error, and the reason is that that column vector now is not compatible in size with the P matrix. So our original first step here is failing because it's not compatible. So one way within Matlab to force it to be compatible is to use this construct. So it doesn't matter what variable x is. So I'm going to define a new variable x equal 2, 3. And I'm going to take the transpose of it. So now it's a column vector. If I want to force that to be a row vector, what I can do, the obvious thing here is to take x, which is now a column vector, and take the transpose of it. The problem is I don't know to start with. If it's a column vector, that'll work fine. But what if it was a row vector? If I take the transpose of a row vector, then it becomes a column vector. So it's like a switch going back and forth. So to force it to always start as a column vector, what you can do is, I'm going to go back and now redefine x to be a row vector. If I want to force x to be a column vector, I can use the syntax within parentheses of a colon, and what that does is it forces the result to be a column vector. And now I can take that forced column vector and take the transpose of it and turn it into a row vector. So in my function handle, I've added that additional feature to my original x use, and that all that does is to indicate that I'm forcing it now to be a row vector by first squeezing it into a column vector with the colon, and then using the transpose operator to force it into a row vector. So now it's compatible with the P. And then having done that, now I can go back, and what failed before, oops, it's still failing. I'm not sure. I think it's because I didn't actually execute this. All right, so I've redefined my function handle, and now it works as expected. So I've done all of this at this point. And then the last thing I'd like to just mention is that in terms of defining this function handle, assume that something like this is so convenient that you would like to be able to use this as a function as opposed to having to define this function handle in all cases. Well, we can do that by, in this case, we're going to create a Matlab function, and it'll be called mySumDistance, and it'll have two input arguments. The first is the x point, and then the second is the p-value. And essentially what this mySumDistance is going to do is just have inside of it this function handle. But by making it a function, I don't have to go back and always redefine this function handle value. So it'll be a convenience. So if you look over here in my current folder, you can see that I've actually already created this function. So it's called mySumDistance. It has these two input arguments, and then sumd is the output argument. And this is a function as opposed to a script because there's this keyword function, which is indicated in blue. And then in a function, essentially all the work that is being done is this line of code right here, which is the same as what I had defined a function handle. But here I'm just doing a regular assignment. Here I'm indicating a semicolon at the end because every time I call this function, I don't want to see results returned to the command window. So I put the semicolon there so I don't have to see anything that executes inside the function. And then it's running this and then assigning it to sumd, and then that is what is returned by the function handle. One thing you can do in a function to make it useful is, just knowing the name of a function is in many cases not useful because you don't know what are the input arguments and what would be the output of the function. So Matlab has the ability to add help information. And the way that is done is after the line where you define this function, the output and the input variables and the name of the function, you can define any number of comments, and the comments are indicated by a single % sign. as opposed to the double ones that are used to indicate cells in a script. So just a single %, it turns green, and you can then put any helpful information about the function. So what I've done here is the first line I've indicated the name of the function, and then just a short description of what it does, calculates sum of distances. And then after that, I indicate the syntax for calling it, and then I define what are the input values, x and p. I also could define what is the output value. You can essentially put whatever you find convenient there. And there's no real standard necessarily, but at least in terms of the Matlab functions that I create, I pretty much try to follow this way of showing the user how to actually use the function and what are the different input values. Notice that once you stop doing a contiguous set of comments, that is everything that shows up in the help information. So if I have a blank line and now I do another thing like just the word hello, when I type help, it doesn't display that. So it's every line that's contiguous after the function, that is what is returned as help. So those are sort of the elements of the help of the function itself. I can go and now do, which I have a cell here that I already have that, so I'm going to execute this help. And what you can see is it actually displays everything that was in that definition of the function. So when you're first using a function, if you're not sure how to use it, it's helpful to do just the command help and then the name of the function. Like one of the other functions we were using was the sum command. And remember there was that option of a second input argument to indicate what dimension you want the summation to occur. Well, we could look at the help information. You can see for this function there's a lot of help information provided. But essentially it starts right here. Notice that in Matlab they use a slightly different, they tend to have much more verbose help information. So there's a little bit more, there's a lot more information here than I would typically provide. I try to be a little bit more concise. And what they're doing here is they're showing that one way of using it is the way we originally used SumX, with just a single input argument. But it kind of is telling you that it's going to be doing it over just the first dimension. So here it shows you that there's another option where you can specify sums along a particular dimension of the array. And this is the one that we ended up using to force it to sum each row of the matrix. And then notice that there's all these other possibilities. And then also at the bottom, they have an example of using the function, which again is very helpful. You can look at it. One thing I find very helpful is that when you see an example like this over here in the command window, if you want to see how it actually works, you can just highlight all of this, and then if you right click and do evaluate selection, it'll actually show you everything that executes. So it's a nice way of being able to very quickly and easily see how something works using the information and the help. And you'll see that in the functions I've created for the ones that are more complex, I also have included examples. So that's a really nice way to kind of get an idea of how things do work. Another format for help information is the document command. And what this does, I'm going to go ahead and execute this. And what this has done is had this pop-up window that's been created. And what this pop-up window does is give you a nice, better formatted version of the same information that's in the help and typically additional information. So this is a even more informative set of help information about the sum command. And this is available for all of the functions in Matlab and also all of the user-created functions. So if I want to look at the my sum distance, if I do doc my, and then if I forget the name of my sum, if I do my sum, and if I hit the tab key, notice that it'll come up with suggestions to complete what are other matches. So in this case, if I scroll down, I'm just hitting the down arrow key. I see the name of my function. So that's an easy way of doing tab completion. Now if I click on it, I get my same help information. Notice that it's not formatted as nicely as the sum, but again, it's a nice way of very easily being able to add help information for a user or even for yourself. If you're going to be using a function again and it might be several months or years before you use it, it's nice to have that help information to be able to kind of jog your memory. So then last thing for this video would be just a short description of actually using this my sum function. So here I'm just going to be calling it. In this case, this depends on what is the value of x. And that value of x was the 2, 3 value. we can here multiply the p-values by 2, and that essentially doubles the sum of the distances. Here we can pick 0 as a starting point. And here, even though we've made this into a column vector, because of this squeezing and transpose operation, it still works within our function because our function has that same construct. So this ends our first video, and any questions, I would recommend looking at the basic concept in Matlab, which has, I think, a more detailed explanation. In particular, the function handle is described in more detail, and also the Euclidean distance example that we've just covered is also described in detail within the basic concept handout.